Okay, so let's look at the first factor that affects speed of reaction, which is the effect of concentration. Okay, so how does concentration affect speed of reaction? Concentration basically refers to the number of particles per unit volume. So if you have low concentration, means you have less reactant particles per unit volume, as seen on the left here. And if you have a high concentration, means you have more particles per unit volume, as seen on the right here. So at higher concentration, what you realize is that there are more particles per unit volume. Hence, there's an increased frequency of effective collision. Because with more particles, there will be a higher chance for the particles to collide. And when there's a higher chance for particles to collide, there's a higher chance for effective collision to take place. So remember, the term effective collision is important. So speed of reaction increases. So what you need to realize is your explanation must first state what is the factor. Second, what happens to the particles that are present. Third, what happens to the frequency of effective collision. And fourth, what happens to the speed of reaction. So these 4 steps here is how you explain speed of reaction, how a factor affects speed of reaction. Okay, and you always follow these 4 steps. So for example, for low concentration means 1, you state what is the factor. So low concentration. And 2, you state what happens to the particles. So means there is less particles per unit volume. Okay. 3, what happens to frequency of effective collision? So there's a decrease in the frequency of effective collision. And 4th, what happens to speed of reaction? So there's a decrease in the speed of reaction. So you follow 4 steps, okay, to answer this question. Okay, so let's look at example. Okay, so for example, if you have this reaction where magnesium reacts with acid to produce hydrogen gas, you can actually track the speed of reaction by measuring the volume of hydrogen gas produced per unit time. So let's say you do 2 experiments. Okay, just focus on curve 1 and curve 2. So for the first reaction, okay, you are using 1 mole per dm cube HCl. For the second reaction, you are using 2 mole per dm cube HCl. So obviously, this one is of a lower concentration, which means you will have a slower reaction. Okay, so with a slower reaction, you will have a gentler curve. Okay, so you can see here curve 1 is gentler. Curve 2, you're using 2 mole per dm cube of hydrochloric acid, means you have a higher concentration, means you have a faster speed of reaction. So you should have a steeper gradient, right? So 1, when we look at the effects of factors on speed of reaction, right? The first thing is we look at the gradient. Okay, so first thing we look at is the gradient. Okay, is it steeper or is it gentler? Second, we look at the height. Okay, that means the final amount of reactants that's being used or the final amount of products that's being formed. So the height is affected by the amount of limiting reagent. So if I look at this reaction, hydrochloric acid is used in excess. Means your limiting reagent is your magnesium ribbon. And since you are using the same mass of magnesium, means you have the same amount of limiting reagent. So even when you change the concentration of acid, which is used in excess, it will only increase the speed. It should not affect the amount of product formed. So as reaction proceeds, concentration of hydrochloric acid will decrease, amount of magnesium will decrease, reaction rate will decrease. So for both graphs, you'll see that the gradient decreases. But finally, the one that's used up is magnesium. So in both reactions, magnesium will be used up, and because the mass of magnesium is the same, so the volume of hydrogen gas produced will be the same. Okay, so you end up with the same height. Now, if I change this experiment, okay, same, I measure the volume of gas per unit time, and same, I use 1 mole per dm cube of HCl versus 2 mole per dm cube of HCl. Okay, 1 mole, 2 mole, 1, you realize the gradient of the graph is different. Okay, with curve A having a gentler curve because the speed of reaction is slower, and curve B having a steeper gradient because with higher concentration, you will have faster reaction, hence a steeper curve. But in this case, you're using excess magnesium. Means your limiting reagent is your acid. And if limiting reagent is your acid and you're changing the amount of limiting reagent, it will change the amount of product form. So in this case, if you increase the concentration of your limiting reagent, which is your acid, it will also increase the amount of product form. So you will have more hydrogen gas being produced. Okay. To take note, effect of concentration only applies to solutions, not solid, because we only can change concentration of solution by either dissolving more solute or dissolving less solute. Okay, not for solids. Okay, so that's the first factor, which is concentration. Second factor is effect of pressure on speed of reaction. So for pressure, it will only affect gases, okay, because you cannot change the volume of solid and liquid. Solid and liquid cannot be compressed. Only gases can be compressed, so you can increase or decrease the pressure by exerting or releasing pressure. So again, the 4 steps. First, you identify what's the factor. Next, you identify what happens to your particles, reacting particles. Third, what happens to frequency of effective collision. And fifth, what happens to speed of reaction. So you realize that at higher pressure, basically what you're doing is you are exerting pressure and hence compressing the volume. So you will have more particles per unit volume, okay, because at higher pressure, you're actually pushing the particles closer together. So you have more particles per unit volume. More particles per unit volume, it will lead to an increased frequency of effective collision, which will then increase the speed of reaction. On the contrary, if you decrease pressure, okay, let's look at decreasing pressure. So if you go the other way around, first, decrease pressure. Point 2 means you have less reactant particles per unit volume. Which means you have decreased frequency of effective collision, and hence you will have decreased speed of reaction. So you realize it's again the 1, 2, 3, 4. 4 steps to explain how this factor of pressure can affect the speed of reaction. Okay. Third factor, particle size. Okay. So when you have smaller particle size, basically what you're doing is, say you have 2 blocks that's of the same mass, okay, but one block you have it as one big particle, the other block, you cut it up into 4 smaller particles. So still same mass because this is 10. This is 2.5 times 4, to 10 grams. But your total surface area, you realize, will increase. Okay, because over here you have more exposed surface, including those inside. Okay, those inside here. So the smaller the particle, okay, the smaller the particle, that's the factor, right? What happens to your particles? You will have increased surface area for reaction to take place. Third, what happens to your frequency of effective collision? It will increase, and hence fourth, speed of reaction will increase. So the reverse is also true. One, talk about the factor. So let's say you increase the particle size. Two, what happens to the surface area? Okay, the surface area will decrease. We have less surface area for reaction to take place, and hence decreased frequency of effective collision, and hence decreased speed of reaction. Okay, so if you look at the graph, okay, so let's say you have the reaction that we have done, okay, calcium carbonate in lumps, and then now we do the reaction for calcium carbonate in powdered form. So how do you think the graph will look like? This is for lumps, big chunky pieces. And now we repeat the experiment with powdered calcium carbonate. So powdered means 1, you decrease particle size, means 2, you increase surface area for reaction, 3, there will be increased frequency of effective collision, and hence 4 will increase speed of reaction. So if you have increased speed, I hope you have gotten it, means you should have a steeper curve, right? Okay, there you go, powdered, okay, with a steeper curve. Take note, particle size will only affect solid reactants only, okay, which makes sense, right? Because you can then change the particle size by either having big lumps, chunks, or decrease particle size by having powder form, okay, which solution you can't actually have chunks or powder form. Okay, fourth factor is temperature. Now, temperature affects the kinetic energy that the particles have. Okay, so when you have higher temperature, this is the factor, what happens to your particles? Your particles will have more kinetic energy. So if they have more energy, overall, the particles have more energy. So you have more particles having energy equal to or higher than activation energy. Okay, so 3, it increases frequency of effective collision, and 4, so speed of reaction increases. Okay, so again, it's the 4 steps, looking at 1, factor, 2, what happens to your particles? Your particles have more kinetic energy, means you have more particles having energy equal to or greater than activation energy. So 3, you have increased frequency of effective collision, 4, speed of reaction goes up. Okay, so if you look at the graph, okay, let's say for this reaction between metal and water to form metal hydroxide and hydrogen gas, say I repeat the experiment at 2 different temperatures. One is at 25 degrees Celsius and one is at 35 degrees Celsius. How do you think the graph will look like? maybe give you a bit of time to sketch the graph. Five means you have a lower temperature. So what will happen to speed of reaction? You have a decreased speed, right? Very good. So means you should have a gentler gradient. Okay. So you should have a gentler gradient. Because they didn't say anything about limiting region, we assume that the amount of limiting region is the same. Okay, so they should reach the same height of product form. So this is 25 degrees Celsius. And if you have to do for 35 degrees Celsius, there you go. Okay, because at higher temperature, you should have increased speed of reaction. Okay, so I hope by now you are quite familiar with how you can sketch the graph to represent the speed of a reaction. Okay, finally, the fifth factor is effect of a catalyst. Okay, so what is a catalyst? A catalyst is a substance that increases speed of reaction, but it must remain chemically unchanged at the end of the reaction. So what does a catalyst do? Okay, catalyst basically provides an alternative pathway with lower activation energy so that the reaction can proceed. So when you lower the activation energy, okay, when you have a catalyst, so this is the factor, the catalyst provide alternative pathway with lower activation energy. So what happens is you have more particles with energy equal to or higher than activation energy. This increases frequency of effective collision and hence speed of reaction goes up. Okay, so this is like, for example, if let's say currently the passing mark of an exam is 50. Okay, so if I put the passing mark of an exam is at 50, there will be this number of students that has 50 and above. But if I lower the passing mark to 40, will there be more students who now qualify to pass? There should be, right? Because the number of students who achieve 40 and above will be more than the number of students with marks 50 and above. So this is something like that, where you actually lower, okay, the requirement for reaction to take place. So you lower the requirement, which is activation energy. So initially, the reactant actually has to overcome this huge activation energy for reaction to take place. Okay, but when you have a catalyst, what happens is you lower the activation energy. So you can see it's lowered now. Okay, so you will have more particles that will have energy equal to or greater than activation energy, so that the frequency of effective collision can be increased and speed of reaction can increase. So please know how to draw this diagram. Okay, how do you draw the energy profile diagram of an uncatalyzed reaction versus a catalyzed reaction? Okay, basically the height of the activation energy is going to be different. Okay, so catalyst, please remember, it will change the speed, but it will not affect the yield, because remember, yield is affected by the amount of limiting reagent that's present. And since for catalyst, it is not being used up at the end of the reaction, only a small amount is needed, okay, to speed up reaction. So the amount of catalyst at the beginning and at the end of the experiment should be the same. Okay, so for catalysts, they remain chemically unchanged at the end of the reaction. Sometimes the physical appearance may change a little, but the chemical properties remains unchanged. Okay, they provide alternative pathway with lower activation energy, and catalysts are selective in their action, meaning the catalyst will catalyze or speed up different reaction, specific reaction. So let's say for the reaction of ammonia, you use iron as a catalyst. You will not be able to use maybe other metals, okay, to be the catalyst. And also, iron is then not a catalyst for any other reaction, okay, meaning that the catalyst is actually very specific in the type of reaction it can speed up the reaction. Okay, impurities can prevent the catalyst from working, okay, because sometimes they're inactivated by the presence of impurities. So there are many uses of enzymes around us. One is in the area of bio. Okay, so you do have biological catalysts in living things. Okay, so for example, our human body do contains many types of enzymes that will help in various body functions. And these enzymes are usually proteins and they are specific in their actions. So for example, there's enzymes actually in your saliva that will actually speed up the reaction of changing starch into sugar. Okay, for biological catalysts, they are usually very sensitive to temperature changes. Okay, if the temperature is too high, they will be denatured. If the temperature is too low, they are actually inactive. And biological catalysts are also sensitive to pH changes. Okay, that means if there's any change in pH, they can actually become inactive as well. Okay, so for example here, C is the enzyme for reactant A and B to come together for reaction to take place. But you'll take note that C remains chemically unchanged at the end of the reaction. We also use a lot of catalysts in the industrial area. So this you have seen in the Haber process. You use iron as a catalyst to speed up the reaction between nitrogen and hydrogen. Okay, we have also seen the catalytic converter, the chapter of air, where you use where you have platinum and rhodium as catalysts to speed up the reaction between carbon monoxide and nitrogen monoxide to produce less harmful gases like carbon dioxide. Okay, cracking is a process that you'll learn in organic chemistry, okay, where you actually break down big hydrocarbons, that means hydrogen and carbon containing compound, to become smaller hydrocarbon. Okay, and usually you need a catalyst to speed up the reaction, and the catalyst is aluminum oxide or silicon dioxide. Okay, and last two example on catalysts, which is in the manufacture of wine and alcoholic drink. So enzymes produced by yeast actually help to catalyze the reaction to convert your sugar to ethanol and by carbon dioxide. And even sometimes your washing powder, okay, if you look at your washing powder, some of them contain enzyme like you'll see lipase, protease, which helps to break down or remove stains caused by protein-based substances. Okay, so with that, we have looked at all the 5 factors that affect speed of reaction. 1, concentration. 2, pressure. 3, particle size. 4, temperature. And 5, the presence of catalysts. Okay, so please remember how to explain the different factors and how they affect the frequency of effective collision and hence how they affect speed of reaction. We have also seen how then these factors affect the graph. Okay, whether the graph will have a steeper or gentler gradient, and also whether the graph will have a higher or lower amount of reactant or product that is left or produced. Okay, so remember how to sketch your graph.